So we're trying to approximate f of 102, and I think we came up with sort of a conceptual way of doing that, if you remember. This is good. We should do this every once in a while. Take like a homework problem from like 2 months ago and see what we have. Sam, thoughts or ideas?
Well, I think you could say it's like local linear.
Okay, so it has local linearity, where it's locally linear. Locally linear. Okay, so keep talking.
So since it has the derivative of 3 at 100, you can kind of set it up as like I guess like a linear function.
Okay.
And just, and since it increases by 2, it would just be an increase of 6.
All right, so this tells me the slope is 3, so 102, since it goes up by 2, probably, so if f of 100 is 35, our guess would be that f of 102 would be 6 more, 41. Is that what people remember? Okay. All right, so that's great. And it's a pretty conceptual, intuitive approach to it. And what I'm going to do today is talk about a little bit how to formalize it and how we can use it to approximate values that are close to a number. And certainly I think we would agree that when we approximate using the tangent line, the closer we are to a number, the better off we are, right? Some people might argue like, wow, how do you know that the slope didn't change dramatically between 100 and 102? You know what I mean? You really don't. It's definitely an approximation. But if I asked what was like, f of 100.1, right, the slope probably didn't dramatically change between 100 and 100.1, although it could have. I'm not saying it didn't, but the closer you are to that value, the more accurate you would think the tangent line is. So I'm going to try to formalize this a little bit. If we have a point like, can I do like, let's see, do you want me to do x comma, so I want to get to the point where I can say a comma f of a. You want me to start with x comma y first? Yeah, here, I'll do that. All right, so if we have a point x comma y, do you agree that y minus y1 equals m times x minus x1 is the equation of a line that contains that point? I guess I should actually call that x1 and y1. Okay, so I'm going to change this around a little bit. I'm going to say y minus y1 is equal to the derivative of x1. Sorry, the derivative at x1. Is that okay? Instead of saying slope, saying the derivative at the point. And finally, I'm going to change it to plus, just get it all on one side. Is that okay? So, sorry, you don't have to write it all down. I apologize. I'm going to write something, well, if you want to, it's okay. I'm going to write it down again, and I guess if you already wrote it down, you don't have to write it down in different notation. But the way you might see it and the way it probably is in your book, instead of a point x comma y, there's probably a point like a comma f of a. Is that okay? So, and instead of using, we might say y minus f of a equals m times x minus a. But instead of y, we might actually say f of x. Is that okay? And instead of m, we might say the derivative at a, not the derivative of x, but the derivative at a. Which reminds me, were you the ones that did this? I think you were. Maybe, who was the other class? It was the other class. It was like we had to find the equation of the tangent line, and the derivative was like x squared minus 2 over x. And instead of plugging in the number to the derivative to find the slope, you just plugged in x squared minus 2 over x. No, I knew it was the other class. Punks. Okay, so f of x equals the derivative of a times x minus a plus f of a. That's the equation of the tangent line. And all I really did was manipulate it, switch it around a little bit, and use function notation. So here it is. This is the equation of the tangent line. And if we go back to thinking about Sam's problem that he just did, let's see if I can do that. Let's grab this. Okay. Wouldn't it be nice to know how to copy? Oh, copy. And let's go back one. Wait, where's Sam's problem? Oh, it's up here. I don't need to do that. Okay, fine. So if we go back to Sam's problem, look, we're saying that f of x is the derivative. Well, what's, oh, here. All right, so f of 102, well, what's the derivative at 100? All right, hold on. So 3 times, what's 102 minus 100? 2, plus what was f of 100? 35. So we get 41. Do you see how that's just a much more formal way of doing what Sam said to do? We're just using the tangent line to approximate. Now, look, this is the equation of the tangent line, and what we're really saying is the function is approximately equal to, whoops, holy cow. The function is approximately equal to the tangent line. And that's why 41 is an approximation. It's not the real answer, but it should be close. So David, and then we're going to do a little more practice.
Are we going to have to do that entire formula and do it all out, or can we just still do it like kind of informally section?
If you're feeling okay, like doing it informally, there's no reason to have to like memorize like an equation, but you have to understand conceptually what you're doing. And conceptually what you're doing is you're using the derivative at a point to approximate values at other points. And as long as those points are close, your approximation is going to be close. And you all have gotten to the point where you can actually tell me, for the most part, whether it's going to be an under or overestimate estimate based on concavity. Concavity tells us exactly if it's going to be under or over. All right, so let's take a look at classwork from this chapter. And I think I actually added to the classwork at x equals 2. I don't think you have that on your classwork. So it says, find the equation of the tangent line to the graph at the given point, and then complete the table. Now, with your calculator, it's a little, let's see, let me give you some history. So, back in the day, nope, never mind. It's not even a good, sorry. That's a poor history lesson. It's not going to illustrate my point. Here, let's do it, and then I'm expecting a question from you. A critical question. Okay, so here we have x equals 2, and with the function's x squared, and we know that we actually know this one's easy. When x is 2, f of x is 4, and the tangent line is also going to have a value of 4. So let's find the equation of the tangent line at this point. How do you find equation of tangent line? Don't even think about using your calculator. What do you need? 2 things for a tangent line? Point and slope. All right. Who wants to start? David, give me. All right. What's the point? 2, 4. All right. David, calling someone to find me the slope. Oh, I just knew that they're going to share that same value because that's where they intersect. Because it's supposed to be tangent at that point. Right? See, mine says it and yours doesn't. Mine says f of x equals x squared at x equals 2. Right? No, that's silly. You have some better tools at your I mean, you can, but you have better tools at your disposal. If I ask for the slope, now you tell me. There you go. Good ears. So the derivative is 2x, and I know the x coordinate's 2, so the slope at 2 is 4. Put it all together, and we get. Now I'm going to use point slope form, and I'll go back to like algebra 2. So y minus 4 is equal to 4 times x minus 2. Now, the way we sort of formalized it, it would look like 4 times x minus 2 plus 4. Okay? So, the tangent line, let's evaluate it for 2.01. Let's use the tangent line to approximate the value at 2.01. We can do this in our head. We can do this in our head. 2.01 minus 2? 0.01. 0.01 times 4? 0.04. Plus 4? 4.04. So can you see that the tangent line oftentimes gives us something that's easier to evaluate than the function? Is there anyone here that can do 2.01 squared in their head, just squaring it? All right, go ahead, do your calculator. What do we get? 4.0401. Is that true? 2.0401. So do you agree the tangent line was pretty close? Say yes. Yeah. Do you agree that the tangent line, we actually didn't need our calculator for this? Let's do 2.1. The difference between 2.1 and 2? 0.1 times 4, 0.4. So we get 4.4 for the tangent line. We can do that in our head. We don't even need a calculator. When we actually do the function, 2.1 squared, we get what? 4.41. So again, can you see that the tangent line is close to the function and easier to evaluate? Say yes. Yes. Why is it easier to evaluate? Because it's linear. Linear functions are easier than quadratic functions. There's a whole branch or part of calculus that does approximations, and instead of doing like trig functions, they'll use polynomial functions. Why? Because polynomials are easier. Instead of using fourth degree functions, they'll use quadratic functions. Why? Because quadratic functions are easier. So there's this whole notion in math that models are great, but if you can pick a model that's easier, why not? The problem is that the linear model is not the same as the quadratic model, but close to a point, it's close enough. So close to 2, these two are very similar. Is that all right? Try another maybe. Does someone want to like say it? Or no? Should I say? Yeah, I mean, doesn't this, that's what I was sort of looking for, right? Does this seem like, what is it? Like swatting a fly with a sledgehammer sort of thing? Yeah. Okay. Yeah, is that like, really it's just a tangent line, we know what it does, and it can do some things. I wanted to formalize a little bit because there are sections, particularly in your math book, and this is going to be weird. You ready? Crazy. Wait. Told you. Wait, what? Oh, so not what I wanted. All right, let's see. Try again. There we go. All right, so let's try a different function. We still need a tangent line. If we want a tangent line, what do we need? Point and a slope. All right. Who wants to give me a point? Alicia. 9.3 is the point. As a matter of fact, I'm going to put that in right here. Alicia, calling someone to find me the slope. Why is it they have so much fun? It's not fair. Sure, and when I plug 9 in, I'm going to get 1/2 times 9 to the negative 1/2, which is what? 1 over 162. No. Square root of, this is the 1 over the square root of 9, so 1/2 times, so it's 1/6. So, the tangent line that I have here is y minus 3 is equal to 1/6 times x minus 9. And that's true as long as we're close to 9. So I get 1/6 x minus 9 plus 3. Okay, so it's going to be a little harder, I think. Let's do tenths first. 9.1 minus 9? 0.1, which is 1/10. 1/10 times 1/6? 1/60th plus 3, we get 3 1/60th. What's that going to be? What's a 60th? 0.0016. No. 0.16 repeating. I think that's what it is. You can write 3 1/60th. What happens when you take the square root of 9.1? Is that what it is? You guys aren't. No, it is not. Nice try, Alicia. All right, but I'm trying to show you that they're really close. They're really close. And so again, I sense, because no one's actually even interested in finding this out, that you're unimpressed with the fact that the tangent line's close to the function near a point. And that's, I know, and I was just about to say that this is great. Really what it says is, look, you know your stuff. You knew this. So I'm not showing you anything new and you're not interested. That's great. That means I did my job back then, maybe not now. But way to be. Okay, so this sort of finishes up like applications of the derivative. The derivative can approximate functions close to a point. There are lots and lots of other applications. We sort of took like the top 5 applications of all time, but there are lots of other applications for the derivative. So if you go into medicine or engineering or physics or whatever it is, economics, you're going to find that calculus and the derivative show up again. And I think just, look, knowing how to use it is awesome, but just knowing that it's out there, it puts you like, tons of steps ahead of people who haven't had calculus before and don't understand about rates of change and how important it is and what we do all over the place. So, there's my cheerleading for calculus for the day. We good? All right. Hang out and wait for the bell. Oh, man. Perfect timing.